talk too fast. Okay, I'll go ahead and share my screen. It's a great pleasure to be here. Thanks for the introduction, Arkady. And just confirm that you see my PowerPoint slides here.
Yeah, we can see it well.
Very good. Okay, super. So yeah, so I thought I'd modeling human AV, as in automated vehicle instructions for safety and acceptance of automated vehicles. And on Arkady's recommendation, I prepared material for about 30 minutes, but I've also put in a couple of places during the talk when you might want to ask questions. I mean, you can stop me at any time, basically, but I've made a couple of breaks midway as well for questions. So yes, I'll go ahead. I thought I'd start with this kind of picture. And what this picture shows for the purposes of this presentation is basically traffic with a lot of people, right? So people in cars, people on foot, people and various kinds of vehicles. Because in relation to automated vehicles, it's now becoming increasingly clear that one of the main reasons, or maybe the main reason why automated vehicles are not sort of getting deployed on such a big scale so rapidly as we thought maybe a few years ago, is because there are people in traffic, right? There are people on roads, and these pesky little humans are quite hard to... What's that, sorry? The sound? Sorry, what was that, Arkady?
No, that's fine. That's fine. I was checking
okay.
if everybody can hear you. It's fine now.
Okay, perfect. Just stop me if it breaks up. Yes, yeah. So these humans in traffic are quite hard to understand and predict and so on, and that is a big challenge for automated vehicles. So one kind of question that we might ask, a very general question, is how can we make AVs, automated vehicles, that can successfully coexist with humans? And what I'll suggest in this talk is that one important thing, I would argue, not a sufficient component, but a necessary component, is to develop high-fidelity models of human road user behavior. I'd argue that we need that as one of the things to be in place to make AVs that can successfully coexist with humans. Hopefully you'll understand what I mean by that by the end of the talk. And then more specifically, what kinds of models do we need? And there I'll argue that we need, I think, a combination of models that are data-driven, machine-learned models, and models which are built on more sort of theoretically clear grounds, or mechanistic models based on cognitive neuroscience, psychology, and so on. So that's something like Arkady mentioned that I have worked with a bunch of different people. So both at Leeds and other places. And one part of the talk will be covering a bit of what we've done, a bit of what we're doing now and what we're doing in the future. We think, so those bits I'll generally pass quite quickly. I'll sort of just want to give you a flavor and an overview, and then if there's something you're interested in, you can talk to me afterwards, or check the references at the end of the talk, or ask a question, right? So yes, on the topic of questions, I thought before I sort of go straight into it, I'd just try to connect a little bit with what I think you in the AI Tech project. So for those maybe calling in from other places in Delft, the people who are hosting this talk are part of a project in Delft called AI Tech, working on this concept of meaningful human control of automation. So I thought I'd just put a couple of questions out there at the beginning, either as discussion questions or maybe as discussion sort of questions from me to you, a couple of scenarios. So on the one hand, if you think of a road user who is effectively interacting with an automated vehicle, the road user, the human road user, can sort of understand how the automated vehicle behaves and what it does and why, and is therefore able to affect the behavior of the AV with their own behavior, just like we do in traffic all the time, right? So as humans, we affect the behavior of other humans with our behavior, right? In sometimes quite intentional ways. So to some extent, we can call that humans controlling other humans in traffic, right? In some sense of the word control. So the scenario here with a human that transparently affects the behavior of the AV, is that meaningful human control of automation to some degree? Another question of the same nature, if you think of an engineer developing automated vehicles, who is studying and adjusting how an AV will interact with humans by using computer simulations with powerful, high-fidelity models across a wide range of scenarios. And then the engineer sort of tweaks the behavior of the AV until it seems like the interaction with human is as good as it can be. Is that meaningful human control of automation? Just leaving those with you for now. And then sort of launching straight into the very pragmatics of it all, right? So the reasons why people are holding back on AV deployment to some extent today is that there are risks associated with it. And I would argue that there are two main risks. One is that we cause human frustration. So you might have read news reports on Waymo cars. I think they've been most extensively reported on being sort of disliked by people sharing the roads with them for many reasons. But one important reason seems to be that they're not quite getting the subtleties of local interactions in traffic right. They're not behaving quite like humans would like them to behave in traffic. They get stuck turning across traffic, that kind of thing, right? So that causes frustration. Which leads to bad acceptance of automated vehicles. And obviously another thing which leads to bad acceptance is human injury. That's obvious, right? So, I mean, there's been a number of high-profile cases in the news where people have been harmed by vehicle automation. So yeah, crashes cause human injury, but not only crashes are important here, but also near crashes, right? Because near crashes can also cause human frustration, especially if there are sort of new kinds of near crashes that humans typically wouldn't cause. So those are the risks. That's sort of what's at stake. So it seems I'm arguing that part of minimizing those risks is having high fidelity models of human behavior. And why do I say that? Do I say it because I think we need to make AVs drive like humans? Maybe we do to some extent. That's not my main motivation for it. So this is just an example of some leads research that I wasn't so involved in myself, actually, but where we looked at how humans, for example, leave sort of extra safety margins when passing a parked car, and then looked into to what extent humans wanted AVs to do that similarly. So on some course level, for that kind of thing, we need models of how humans do stuff, but I wouldn't quite necessarily go as far as to say that we need high fidelity models that are very detailed and exact. The other thing that maybe most AV engineers think about when we talk about models of human behavior is online, sort of real-time onboard AV predictions about human behavior, right? So there's a lot of literature on this. This is just one example. So basically, if we have some sensor data about surrounding road users with some history, we try to apply some algorithm or method to predict what these guys are going to do in the future, right? Really important for AVs and AV planning algorithms. So obviously, they rely to some extent on models. Models are typically not very advanced, and my interpretation of this literature is that still a big part of the limiting factor is still just things like dealing with the sensor data and uncertainty in that and so on. So of course, if we had super good high fidelity models of human behavior, they would be useful for this kind of thing. But that's not the sort of prime concern at the moment. But I think one area where it is a prime concern already, and perhaps not sufficiently appreciated, is as agents for virtual environments for simulated AV testing. So you may or may not have heard that people are talking about the importance of simulation-based testing. So basically running lots and lots of simulated miles or kilometers of driving. So the image here is from a Waymo report. It's their platform where, for example, they can replay log data. So the surrounding road users might come from logged data, logged scenarios. That an equipped vehicle, either driven by a human or an automated vehicle, have collected these log data. And then as soon as you update your algorithms, your software on the automated vehicle, you can rerun all of that log data to see that you haven't introduced something which causes strange or dangerous situations, right? So that's really important. But of course, as soon as your update changes the behavior of this logged vehicle, even the slightest, right? The surrounding log users, they're sort of just being replayed open loop. So there's no interaction. So if you change your behavior as an AV here, you don't know how the others would have responded to that. So that's the point where you start needing models. And people have been talking about it, but unless there is lots of stuff happening under industry hoods that isn't being published at all, to me, it seems like just as it was 3 years ago, we don't know how to model how humans interact in traffic. It's a really complicated problem. So in one sense, it's fair to ask, these simulations are important, and people are saying that's how we're going to know that automated vehicles are safe, because we're going to run billions of miles of simulated testing. But if there aren't really any humans in that simulated testing, is that really going to cut it? Is that good enough? Okay, so I mentioned data-driven models at the start. And I think these are super important. There's a lot of work on this as well. This is one example where Behani et al. Extracted trajectories from camera data and then used sort of imitation learning, machine learning algorithm to create agents that would behave as much as possible like the observed humans did in this situation and other traffic situations. So these methods begin to achieve realistic looking routine traffic, which is great, and I think it's really important. But I think there are also a couple of challenges in relation to specifically those two main risks I mentioned at the start. Right. So when it comes to behavior of humans in near crashes and crashes, it's important to realize that in any real traffic data set, and these models, these machine learned models, need a lot of data from real traffic, right? Even if you have lots and lots of data, near crashes and crashes are going to be very, very rare. So it's going to be very hard to know to what extent your models here generalize well to near crash situations, which arguably are very important, right, for the simulated testing and verification. And the other thing is with respect to human behavior in local interactions. So how do you know that these models are capturing the important subtleties of behavior? So it's sort of, when you squint a bit and you look at these simulations, they look sort of like the real thing, but on the detailed level, how can we know that the important bits are gotten right? And my suggested answer, as part of an answer, is that we should complement these black box machine learned models with white box neurocognitive models, sort of models based on cognitive science and similar. And that will then have the potential to provide us with some insight into how mechanisms generalize, addressing this issue of generalization to near crash behavior, which, as Arkady mentioned, is something I and others have done a lot of research on. And it sort of gets us into this scientific frame of working, right, where we can have a model and a hypothesis, we can run a controlled experiment, testing it, parameterizing it, and so on. And that ultimately leads to something like understanding, right? We start to understand maybe what the important subtleties of local interactions are, for example. And I think we can't really solve the problem of getting subtleties of interactions right without sort of trying to understand it to some extent. Black box models, really important, but we also need to have some understanding. Okay, so that was sort of my main little first part, my first little part. So I thought I'd just pause for a moment here and ask if there are any thoughts or questions thus far. And if not, I'll continue straight on.
So just if you have a question, please raise your hand virtually, not in real life, or just post it in the chat. And we'll allow for 20 seconds. If there are no questions, we'll go.
Counting to 20 in my head. Maybe continue, Arkady, and we can catch up later. I have another slot on at the end as well, yeah? Okay?
Good.
Cheers. Okay, yes. So let me then say a bit about what I and others have done to start to sort of make models and modeling frameworks for these kinds of things. So one of the first things I did in driver modeling research was to try to get a framework that could cover both routine driving and near crash driving. And what I tried to do there, because I was interested in how the brain does stuff, right? How humans actually do things. I tried to steal as many good ideas as I could from psychology. So like perceptual heuristics, this idea that there are specific sort of salient pieces of information in our environment that we make use of as part of heuristics when we control our behavior. and decision-making mechanisms, especially in terms of evidence accumulation, that you may or may not have heard of as a sort of model of how the brain makes decisions. It adds together bits of evidence until it reaches a threshold where a decision on what to do is made. So there is both behavioral and neurophysiological support for that kind of model. And then also another part that I've made use of is the idea of motor primitives, that you can, even behaviors that are sort of look like they're continuous and sustained over time, can be broken down to minimum building blocks of control of behavior. So then I pieced those bits together into a framework that sort of explains routine driving and near crash driving in the same language. So whereas conventionally routine driving is often described as sort of closed loop, short delay, well adjusted, or even optimal control, if you look at how near crash driving it's described as open loop behavior without concern of how something is sort of playing out after you've done it, with long random delays before you do anything, and under and over reactions, right? Maybe you brake too little, you steer too much, that kind of thing. So anything but optimal. Whereas in practice, obviously they have to sort of be the same thing. There's no sharp edge between them, right? It has to be a grayscale of some sort. Then, very briefly put, you can sort of tie these together by positing that there are these intermittent motor primitive adjustments that are decided on by accumulation of evidence of various kinds, and you use maybe perceptual heuristics to determine how much control to apply, and those heuristics might be well adapted to routine driving, but when you sort of push them out into a context, a near crash context where they were not sort of learned for, they might be severely suboptimal. And sensory predictions also plays into this. So then what you can sort of get out of this are models that can be used, for example, as a sort of cognitive crash test dummy, right? So that's something I and collaborators have been publishing on a bit. So yeah, so I'll mention some examples of what we've applied it to, for example, explain routine and near crash braking. So we've shown that among a bunch of different models that we compared, this kind of accumulation model was the best one at explaining brake response time distributions in normal traffic, sort of car following traffic. But also applying the same sort of framework and in even more detail, actually, to also explain the brake control to some extent. We looked at the naturalistic data from the SHARP2 data set that you might have heard of, a US large data set with actual crashes and air crashes in it, log data. We can also show that the sort of model probability distributions can be we can find model parameterizations that are sensible and that help explain this near crash braking as well, and also sort of explain additional parts of it that were difficult to understand without a model. So that's a preprint out right now with a link there. And another type of extension of this is to pick up on the sensory prediction aspects of it that I mentioned, to connect it with predictive processing types of models and apply it to automation failures, right? So if you're driving a car that is controlling your speed and the car in front brakes, which means that normally if you were not doing anything and the system wasn't doing anything, you'd see a visual looming of this obstacle rising like this black line. But since you know that you have an automated vehicle, you're expecting the looming to rise slower as the sort of system is taking care of the situation. But what we were then suggesting was that the kind of delays that you see in responding to these so if the system fails and it doesn't actually brake for you the way it's supposed to do, what typically happens is that drivers do not respond as quickly, of course, to the lead vehicle deceleration as if they had been in control themselves. But we can then explain this by assuming that what they're responding to now in this automated mode is the prediction error between what they were expecting to see for a working automation compared to what they actually saw. So then if we fit a model to the manual braking of drivers, we can just, without any further parameter changes, just apply this prediction error thing and get pretty good predictions of the delay responses when people were experiencing these silent automation failures. And yes, another sort of benefit of doing these kinds of models, which link together with cognitive science and psychology concepts that have been studied on a sort of more basic component level, is that you can also connect it to things like neurophysiology. So we have been starting to do some work on for these types of driving related tasks, see if we can, like others have for more basic tasks, if we can see traces of these kinds of evidence accumulation processes happening in the brain. And it turns out we can to some extent. Obviously, it turns out to be more complex than one might have hoped from the start, but we do see the same kinds of signatures as you see in more typical lab-based tasks. Yeah, so this is just some EEG data. I won't go through the details. You can ask me if you want to. Okay, so that's sort of work in the past and current work focusing on sort of one vehicle at a time, right? But now we want to generalize this to interaction. So the first thing we did in one project, which is now coming to an end, it has its final event tomorrow and Friday. I think you can, I don't know if you can still register. Ask me, if you're interested, ask me afterwards. You can Google Interact project on interactions between automated vehicles and humans, and we did some modeling work in there on, for example, a pedestrian crossing scenario, also a sort of driver turning scenario. We spent most effort on the pedestrian crossing scenario, and what we did in VR experiments had people cross the road in front of oncoming vehicles that behaved in different ways. Every little panel you see here is for a different scenario, a different way that this vehicle was approaching the pedestrian who decided to either cross before or after the car, right? So then you get these rather complicated probability distributions, which are often bimodal. So either you sort of pass before the car early, or there's a gap here in the middle where it's too scary, you want to pass, or you pass afterwards, and also when it's decelerating to stop, same kind of thing that you might recognize from real traffic, right? Your own behavior, at least I tend to do that quite often. You see a car that, in hindsight, you understand was stopping for you all along, but you end up waiting until it has come to almost a complete stop before you pass. So we saw that in these experiments as well. We started playing around with how to maybe account for these kinds of behaviors models, and we had some rather complex ideas of stringing together a bunch of different decision-making evidence accumulation units, making perceptual decisions on the nature of, I can make it across before the car, or the car is stopping for me, which then would excite or inhibit action decisions like I am crossing now, right? And we also tried some simpler versions with just a single evidence accumulation unit, but with the same kinds of inputs. And what we found was quite nicely that all these models, even the simplest ones, actually work quite well to capture the overall gist of these very complex probability distributions. And in the current work that we haven't yet published on, we're getting even sort of better fits and nicer models out of this. So that's good. And yeah, so then tying back to this kind of scenario I mentioned in one of my portal questions in the start, this engineer who's using simulations to tweak AV behavior. So that's one sort of illustration of that kind of idea. We can take this first model for this rather simple pedestrian crossing scenario, and we can start playing around with it in simulation, right? So this is now, I don't know how out in slightly different waited until the car loose this case. So then we can just pedestrians get stuck. Okay, that was sort of an overview of stuff we've done. I don't know if you've received any questions at this point, Arkady, or if anyone in the audience wants to chip in on anything.
Yeah, I just wanted to mention that for the last minute or so, when you explained the model simulations and you had animations there, we couldn't really hear you. It seems like your bandwidth is limited, and it was all taken by this nice animations there. So we couldn't really hear you for the last slide. Other than that, it was great,
Okay.
and I thought we already might have some questions by this stage. Please raise your hand or type the question. Yes, Sarvesh wants to speak. Sarvesh, can you unmute yourself?
Yes. Maybe I put on my camera as well. Hello, Gustav.
Hi there. Yes, we can see you.
Yeah, thank you very much. I'll keep it short. I wanted to know a bit more about the looming prediction model. I didn't really understand how you predicted, how you created the predictions about what they think the future states of the autonomous vehicle would be.
Gustav, could you hear the question?
Sorry, I made the mistake of starting to go back through my slides, and I hit those animation slides. So I understood that you wanted me to. I understood that you wanted me to go into the looming prediction model. Yes. But then I didn't catch your question. So if there was more to the question, could you please repeat it? Sorry.
No, not really. So I just wanted to understand the basics of the model, at least, as to how you make the predictions about what the humans think the autonomous vehicle would do in the future. That's what it does, right?
Yes.
Yeah. Okay.
Yes. Okay. Let's see. Here we are. Yes. So basically, the basic model essentially just take this visual looming. This it's sort of the relative optical expansion rate of this car in front of you. How fast, relatively speaking, it's growing on your retina over time. So that's described by this black line, and then the model just accumulates that basically to a threshold with some noise, and that's what gives the normal behavior. And then the key bit here is to run some simulations with the system when the system is in control and when it's working like it should. So the looming that a driver would see when the system is working as it should is this dotted line here. So that's for a lead vehicle deceleration scenario of the nature that was studied in this study. The driver, from the training and maybe from real world experience as well, would have learned, is the assumption, that when the system works, I will see a visual looping signal which looks like this dotted line. Sorry, so yeah, I was pointing to the wrong line before. So the actual, the normal looping signal is the dashed one, sorry, obviously. So it's the dashed one, and the one that is the case when the system is working as it should is the dotted one, and then the prediction error between the two. So the difference between these two lines is the black line down here. Sorry, I was pointing to the wrong one, which, as you can see, naturally sort of rises more slowly, which leads to this prediction of slower brake response time. When we just feed it to the exact same model that we parameterized on the manual braking behavior, we hit quite nicely these brake response times that we saw in the study. Was that a bit more clear?
Yeah, that is very helpful. Yeah, thank you very much.
So we have another question from Nick Beckers here in Delft as well. So Nick, do you want to ask a question in person? Because you posted in the chat, right?
Sure, can you hear me?
Nope. We cannot hear you.
Yeah, sound was very low, I think.
Yeah, because
hear
it's my
some?
microphone. Because Nick is in the same room with me, so you can hear him
Okay.
through my
Okay.
microphone. Maybe that's an
Okay.
option, actually.
All right. Can you hear me now?
Yes.
Perfect. So yeah, I asked the question in the chat already. Thank you first of all for the great presentation. Super interesting already. So I was wondering, well, you can also read the question in the chat, but so most of these behavioral models are based on of the interaction with a static actor, for instance, like a car coming towards you with like a fixed speed or anything. So what are your thoughts on, when these interactions actually become dynamic, so you influence each other, so people like the AV and the human adapt to each other? Do these behavioral models still hold? So what do you think about? What are your thoughts about that?
I think it's a super important question, and definitely what we've done so far with these road crossing models does that not extend to that. So we're just modeling one agent, and then we're sort of, like you said, in those studies, for example, but also in our simulations, we're sort of controlling what the oncoming car is doing. So obviously, then what you need is to have models of both actors, right? And that would then, I mean, so the pedestrian model in this case is, you could argue that in some ways it is sort of taking into account what the this oncoming car is doing. So if you had a model of the car that can either decide to pass or decelerate in different ways depending on what the pedestrian does, this pedestrian model is sort of equipped to respond to those behavioral choices of the car, right? But then you also need a model of the car and the car driver itself, or an AV, right? So that's stuff we're starting to broach now in currently ongoing projects, but it is an order of magnitude more challenging. And for, like you said, I think you mentioned sort of studies, human in the loop studies. I think that's definitely something that we want to do more of. So we have started doing in LEED, since we have this nice benefit of having a super nice pedestrian simulator, a cave, as well as sort of head-mounted display type pedestrian simulators. We also have a few different very nice driving simulators. So we've started connecting those together to run sort of co-simulations where two humans can interact. So that's one method of trying to get data on that kind of thing. But of course, then the complexity of setting those studies up, as you can imagine, is also an order of magnitude more larger. So yeah, not an easy problem, but a very important one for sure.
Great, thank you. Yeah, looking forward to reading about it. So
cool. At some point.
So good. I think we're running out of time for the questions for this part of the talk. So do you want to keep going?
Yes, let's do that. And I'll just skip past animations. Yeah, it was a good prioritization of Jitsi to prioritize the graphics over my voice. Yes, so a little bit like you were saying in this last question here, right? There's lots more to interactions in traffic than what was covered in these slides. So this is just a figure from a recent, paper. I'm thinking too much ahead. A recent paper where we still wanted to look a bit more conceptually at I mean, what is this beast? What are interactions, right? And try to, so this is not a modeling paper. It's more of a concepts and terminology paper where we defined space sharing conflicts as an observable situation from which it can be reasonably inferred that your road users are intending to occupy the same region of space at the same time in the near future. Where we then can also define an interaction as a situation where the behavior, at least to road users, can be interpreted as being influenced by a space sharing conflict between the road users. So the key thing, right, is that the people are competing over space here, or negotiating or collaborating in some cases. And if you look at what behaviors people then exhibit, I mean, you can see to the left here a bunch of different types of space sharing conflict that generate interactions, and to the right you see different types of behaviors. If you look at the literature, what people have seen and studied, different types of behaviors to either achieve own movement or perception, moving around, looking around, but also behaviors that sort of seem to have the purpose of signaling about own movement, signaling about own perception, and requesting movement or perception from others. And then also behaviors for signaling appreciation, so the thank you or the FU to the other road users. So yeah, you can map out stuff that's been studied in studies and so on. So these crosses are just examples from papers of what people have looked at of these different categories of behaviors, which can then overlap, right? So when a pedestrian is adapting its trajectory to yield to an AV, it's both movement achieving, but it's also movement signaling. So one aspect of this, which again connects to that question of how do they adapt to each other, is when you start to think about strategic behavior or game theoretic behavior, right? So that's game theory is the typical thing that you get into, right? If you're thinking that agents in the world are trying to maximize some benefit for themselves, they're trying to get to the goal on time and safely, for example. But then if you have multiple actors doing that at the same time, for example, competing over space, like I just said, then you get into game theoretic type considerations, right? So that's something we have done a bit of in Leeds with a PhD student called Fanta Camara, where we've been able to formulate sort of simple game theoretic versions of some of these scenarios. And also Fanta has also been able to sort of estimate some of the payoffs in these situations, sort of how much people prefer progressing over avoiding crashes, sort of how much crash risk you can accept basically to get some progress, which is really interesting and elucidates a lot of interesting things. But there's a further complication to it, though, which is that we know from sort of basic studies of game theory type situations that human behavior is quite often not game theoretically optimal. Even when we can know exactly what these payoffs, these cost functions, value functions are, people don't always behave like Nash said they should, right? And often we don't know the payoff matrix even, right? So the humans value strange things. So sometimes people aren't just prioritizing getting to their goal without colliding. Sometimes people seem to value actually being polite or helping each other. So yeah, there's challenging things to get into these rewards or value functions. But nicely enough, again, there's been on the basic level quite a bit of work on, obviously, in psychology on why and how people are not game theoretically optimal and social orientation in game theoretic type situations. So I just highlighting here one interesting recent paper which connects together game theoretic reasoning with accumulation models, where you can quite nicely sort of follow how an agent reasons sort of iteratively. If I do this, then he would do that. But if he knows that I would do that, if he does that, then I should do this instead. That kind of thing. So that's something to maybe leverage. Other important areas for further model development that we need to get into to address these things is human recognitions of actions and intentions and communication. So again, these pedestrian models I mentioned, they do a bit of that, right? So they're recognizing if the car is stopping. We have also, I didn't mention it, but we've also incorporated some of these new ideas of external human-machine indications, where the AV sort of signals with some flashing lights or flashing headlights even to the pedestrian that is going to stop, and that can then affect the behavior of the pedestrian. But if you look at this in a more bigger picture for more kinds of scenarios, you need some more general ideas for how it works, maybe. And then nicely enough, there are, again, from cognitive computational science and computational neuroscience, there is models and modeling ideas that sort of address this kind of thing. This is one example of a model where in a sort of joint coordination task, the agents need to sort of understand what the other agent is doing, or is he going left or right with his arm, and then the agents might sort of exaggerate their movement, like this AV in the simulation did, right? Exaggerated its deceleration to be more understandable, and that kind of thing has been studied and modeled in more basic contexts. Another complication that is important to bear in mind in some situations is that humans can only look in one direction at a time, right? So in some situations, especially if there's more than two actors, you might need to actually get attention and gaze allocation modeling to some extent. Again, there are models out there in the more basic literature that you can consider leveraging and that sort of fit together quite nicely. Again, the nice thing about having this cognitive science based framework is that it's relatively easy. Well, easy is of course not quite the word, but it's feasible to pick these other components up, right? So overall, the contemporary cognitive neuroscience sort of provides the needed components, so that if a modeler is allowed to dream, he might say that maybe we can head towards a more complete neurocognitive modeling framework for interactions in traffic. I won't talk through this in detail. You can look at it later in the slides or the recording and pour over it and ask questions or whatever. That sort of maybe works for multiple agents and for more different scenarios, but can still sort of get these the subtleties of local interactions reasonably right. So yeah, so that's what we're working on at the moment, mainly in a project called Commotion, some other ones as well. We're aiming for more complete neurocognitive models of interactions, and we want to also, as part of the project, investigate the complementarity with more machine learned models. So we're trying to do a bit of both and see if we can sort of benchmark them against each other, maybe sort of get the best of both worlds, that kind of thing. A few months back, we published a green paper, a short one with some more information about the project. If you want to read that, please do. There are also some sort of questions, an invitation for input, so feel free to get in touch about that. So yeah, in summary, I've argued that safe and acceptable automated vehicles are complementing data-driven models of human behavior with neurocognitive models. And we, and obviously lots of others as well, are working on the challenge, and just very happy to have input and further discussion on it. Thanks. And any questions? And let's see, I mean, maybe I should open this chat window. Derek would like to speak. That's fine with me. I'll open.
Yeah, great. No, thank you very much. That was it was really interesting to get these neurocognitive models aligned with the autonomous driving systems. You only went into it a little bit, but these kind of motor primitives and this sort of broader vision of how the brain can handle some things very quickly. I wonder if there's a more sort of speculative vision that you have for how this research might progress over time.
So with respect to the motor primitive specifically, I mean, sorry, could you just elaborate a little bit maybe on what you're thinking?
Yeah, I guess with respect to motor primitives, or I'm thinking about you know, some of these aspects of cognition that we don't get to very often because they're deep in the weeds of the motor system, central pattern generators and things of that nature. I wonder whether there's a kind of general approach to how you see the co-development of the neuroscience work and the AI work coming together, you know, over a broader time scale. Basically, I'm asking you to speculate a little bit how you see this work and say.
Oh yeah, I mean, you can. I guess you could start from the motor primitive thing, and there's that sort of just branched out in such a multitude of different ways, straight ahead, right? And there's so many directions you can go with it, right? So what I've done with it is basically just look at it from a top. I've used this as my sort of minimal building blocks, and I haven't looked further on. I said, for me, the motor control sort of stops there. I can issue a command, and something makes that motor primitive happen. But there's obviously lots of detailed motor neuroscience work on exactly how that works on a more fine-grained level, right? There's further hierarchical levels beneath that where the neuromuscular system sort of tries to ensure that the desired motor behavior actually happens. And then there's another connection to robotics for sure. I mean, it's not a literature I'm deeply familiar with, but I know that there's been a lot of work on using motor primitives for robotics. I mean, I think there's a lot. I mean, it fits together with this general perspective of hierarchical control, right? So the level which issues the command for motor primitive can very clearly sort of be thought of as one hierarchical level above another. But then I think there are others have said this as well, I'm sure, you can sort of again think of that as having further hierarchies as above where that motor primitive might be part of a more compound primitive, a behavior primitive, right? That sort of launches a set of motor primitives in sequence and turn that's sort of well adapted to a longer sort of longer temporal scale of the context. So yes, it fits together with that kind of hierarchical perspective as well. I don't know if anything of that connected a little bit with what you were aiming for.
No, it does. No, thank you. I'll send you a paper that I came across recently on the hierarchical control of central pattern generators. So it's it's just, there's all kinds of weird things in the neurosciences. It's such a huge field, and this one in particular had some very nice visualizations, and it created I think a kind of practical view of exactly what you're talking about. I guess the place that I'm curious is what are some of the implications that might have for training? I mean, are we trying to kind of do too much at once? Are there sort of these small responses that we'd want to train up and build together? I mean, that's kind of part of my takeaway.
I mean, when you're training the automated vehicle, for example?
Yes, exactly.
Yeah, I mean, it's certainly how I think part of how we think that the human learns to, right? You start with this motor babbling, right? And you get a basic control of your basic motor primitives, and then you start sort of compounding them together to more advanced behaviors. Okay.
I think Luciano
Yeah.
wanted to speak. Luciano, can you ask a question?
Yes, can you hear me?
I can.
Hi, so Gustav, thank you very much. Very interesting presentation. My question goes maybe a little bit follow up with what Nick asked before about this idea of mutual interactions. And there we can have some, let's say, some unexpected emergent properties there. And there I connect a little bit from the work on ethics. I don't know if you're familiar with what's called the naturalistic fallacy. What is the impossibility to connect ought, so what we should do, from what it is. So there's naturalistic fallacy that if something is natural, therefore is more acceptable, but it's very challenged that. So in this sense, how do you see this kind of moral values, norms, and in a broader sense, the moral reasoning for autonomous vehicles? Is that something you consider relevant, or what are your thoughts on that?
For sure, relevant, definitely. I must confess I haven't thought much about how that connects in here. So unfortunately, I tried to turn on my video, and maybe this limited bandwidth that Arkady was mentioning was playing some tricks on me, because I couldn't catch all of your questions or your question. But no, I haven't thought much about the connection between the modeling work and the moral elements. But you were saying something about natural behavior. Sorry, could you?
Yeah, it's called the naturalistic fallacy. So what it means in ethics is the impossibility of deriving the ought from is. So you should not derive what the autonomous vehicle should do based on only what the humans do. For example, take the humans at the standard of what is right, because in this discussion on ethics, they say there are some moral principles or some other things that should also be considered on this aspect. And I'm not really talking about trolley problems, these kind of things, but just some kind of more practical moral reasoning here.
Yeah, I think one possible connection maybe is in terms of sort of what, I mean, I'm not sure that the connection holds completely, but to some extent, I mean, things that we dislike in others, like the things that we dislike others to do, are, I mean, I'm not sure whether that fits exactly with the definition of what's moral or not, but there are some behaviors in traffic that others do, which I would dislike, and I would maybe say that that was sort of an immoral thing to do in that respect. So I think one connection to the models there is that if we are able to get, as I'm hoping, to these more sort of models where this negotiation process is covered somewhat explicitly, this sort of game theoretic negotiation, then in theory it should be possible to say, sort of from a given model simulation, whether the model was happy or not with what the other actor did. So I'm not sure whether that I'm not sure it's true that if the model was unhappy with what the AV did, whether that means that the AV behaved immorally. I'm not sure if that is true, but maybe there's some weak link at least.
Yeah, I can definitely see some connections on also on the moral acceptance of this
Exactly,
system by society. There, I can definitely see some links there. And okay, glad and maybe I'll get in touch with them soon to discuss some other ideas I have there.
Yes, please do.
Okay, thank you very much.
Thanks, Luciano. Really nice question. We also have a question from Xiaomi. I'm not sure if I'm pronouncing the name correctly. Do you want to ask a question in person or post it in chat? No? Xiaomi or Xiaomi? Right.
Sorry, audio's not working.
Okay, says it was not working. Then, yeah, you could type your question in chat. Meanwhile, can I ask a question myself? So,
sure.
Gustav, you mentioned a really important point in the beginning, that you think these neurocognitive models of humans are necessary, but not sufficient, right? I agree, absolutely agree that it's necessary, but I'm biased here, of course. But I was wondering, on your opinion, whether you think the data-driven models that you mentioned are also necessary, or we could get away with them without them, just using neurocognitive models. And if you think they are necessary, then what is your take on integrating, for instance, in the context of virtual simulations of AVs, integrating data-driven models and neurocognitive models?
Good question, thanks. I would say that in theory, they are not necessary, but in practice, they are necessary, the data-driven models, because in theory, we could make fantastic neurocognitive models that sort of capture human behavior very nicely across a sort of vast multitude of different scenarios. But that's just a very tall order. And it'll take some time if it's ever possible, right? So human behavior is just so super complex. So yes, we can make these. I think what we can hope for is to make neurocognitive models that can sort of deal with some local situations with a few actors, and then maybe sort of build a catalog of different scenarios that we can believe that we can address reasonably. But to actually do then these large scale simulated verification and so on, we need models that can scale up much more to a bigger variety of scenarios and so on. And there, I think that's where the data-driven machine learning models can shine more. So we can't be sure that they get every sort of detail right. We can't be sure that they get the near crash stuff right necessarily. But then we can, for those sites, we can sort of complement it with, at the very least, we can sort of do both things, right? That's the simplest way of combining the two approaches. That was the second part of your question. How can we combine them? So the simplest way is just to do both in parallel, right? We can test our AVs both with machine learning models and with neurocognitive models. But then in terms of combining them, we're just sort of scratching the surface of that question, but there's a bunch of different approaches. I mean, so if the argument is that we have too little data of near crash situations, maybe we can generate near crash data with the neurocognitive models. That's one kind of connection. Another kind of possibility would be to sort of look at the neurocognitive models and see if their architecture can inspire the architecture of of the typically neural networks that we would use in the machine learned case, right? So maybe by figuring out some aspects of the neurocognitive models that are important to get right, we can sort of get them into help the machine learned models get those parts right by controlling their architecture. So I think there's some different approaches. Some of them connecting them together a bit more, others keeping them a bit more separate, interchanging this data. But I think we're just sort of beginning that journey.
Good, thanks. Very interesting opinion. So Xiaomi posted that question in the chat. Do you want to read it, or I can read it for you?
Yes, I'm not sure whether the data used from model is from naturalistic data and for a manually driving car. If so, how would it influence when considering the human user's interaction with AVs? What do you think? Yeah, so yes, so I guess so the data we have used has been, for some of it's been from naturalistic data sources, from other it's been controlled experiments. In the pedestrian crossing situation I mentioned, that's been in controlled VR experiments with a car that is computer controlled. I mean, it's not necessarily, I mean, you can either put a little human in there that the participant may or may not see, and then it's sort of, in quotation marks, a human driven car, or it can be an AV, especially if it has those flashing external HMIs. But I do agree, it's an important distinction, sort of, if we, in terms of generalization, right? If we, I think what I'm trying to focus on at the moment is to get to understand human interaction and model that. That's sort of my starting point. But I agree that an important part of it is also to make sure that if the AV then starts behaving a little bit differently from the human in some way or another, that the models also generalize correctly to that. So that's again a sort of a challenge to the data-driven models, right? So if the AV that you're trying to test does something, I hadn't thought about that specific angle before, actually, so thanks for that. Does something differently from what typically humans would do in that situation. How do you know that your machine learned models are generalizing correctly then? And of course, that's something you would also need to test with a more white box theory-driven model as well. I hope that's answered your question to some extent.
Okay. Do we have any other questions? We are technically out of time, but there is time for one question, maybe.
No, that's fine. I'm in no rush personally.
Right. Okay. Maybe I will ask the last question then. Another one. So we were mostly talking about interactions between a human and AV, right? Mm-hmm. Which implicitly assumes that there are two agents here, a human and an AV. So as far as I'm aware, the neurocognitive models, for instance, of decision-making, attention models, they are tested in very limited lab-based situations. So there is very rarely more than two agents, which we can account for in this kind of models. So do you think this kind of generalization to multi-agent interactions is possible?
I would hope so, but I agree. That's another sort of further complication, and how, like you said, these when people have studied in the lab interactions, it has been. I can't think of any paper doing that with more than two people either. When sort of doing it modeling at that sort of detailed level. So yeah, so I mean, I'm certainly trying to, in my modeling work now, try to sort of take height, or whatever, if that's an expression in English, to sort of have ideas about how you could consider multiple agents. But it is a complication in its own right, for sure, and not necessarily one, like you say, there is great support for currently in sort of computational cognitive science. So it would be nice if more computational cognitive scientists address that in the lab, for sure, so we could steal their models for these applied purposes.
Yeah, good. Okay, thanks. Yeah, if there are no more questions, let's wrap it up. So thanks a lot, Gustav, for the really, really interesting talk. I think that this meeting has hit a record. At some point, we had more than 50 people present. So that is something we haven't done before. So this shows there is a lot of interest in what you're doing. Yeah, thanks a lot. That was very interesting and very stimulating. Looking forward to getting into more detailed discussions with you, and also I'm pretty sure that you'll be getting some more emails in the coming days.
Yes, please don't hesitate to get in. Yeah, thanks a lot. Please don't hesitate. To everyone listening, to get in touch if you have thoughts or questions or whatever. And yeah, no, it's been an absolute pleasure. I had good fun, and thanks a lot.
Good. Okay. Bye bye. Thanks.
Bye now.